Okay, everyone, we're on to 7.2, two variable linear systems. So again, we're going to be working with something that you have some experience with in Algebra 1 and Algebra 2, looking at systems of equations where you have two lines, so two linear equations. So imagine situations where you'd have two different real life situations being modeled by a linear rule, and you're trying to figure out the solution to that system. So that's what we're going to be looking at. So for day one, we're going to use some different methods that you are hopefully familiar with. Elimination. I know we talked about substitution in section 1. That's also great for linear systems, but elimination can work really well. And we're going to interpret graphically, just specifically for two linear situations. What does that mean graphically? We have some names that we're going to be using that we'll talk about that. And we'll be looking over a few things as we go through those. So let's jump right in. So what is elimination? What does that mean? So there's some kind of just step-by-step directions that we usually follow for solving a system by using elimination. So as opposed to substitution, where you need a variable by itself. So I'm just going to kind of peek ahead and show you in a situation. So here's a example one. Two equations that are both linear. So we have x and y, first power. We could try to use substitution. So if you take a look at that, you can kind of pause the video. If you wanted to use substitution, we could, but we'd have to do a little work with the equation first. So maybe think about a way that you could do that. So in equation 1, potentially, we could get the y by itself pretty easily. We could just subtract the 3x. We could substitute that expression into the other one. We can solve. Works really well. But there is another method. Maybe you're thinking back on this elimination, what that means. Making opposites, making it such that when you add the two equations together, you eliminate, you get rid of one of the variables. So that's an easy way sometimes when they're in this, what we call standard form, where the x and the y are on the same side, we have all integer exponents, like they're usually pretty easy to work with. So we try to make opposites. That's kind of our quest. So those are the kinds of examples we're going to take a look at today. So kind of first things first, we need to get coefficients, or the number parts of the terms that are opposites, but sometimes they're opposites already. A positive y and negative y, great, you're ready to go. A positive 6x and a negative 6x, they're ready to go. If they're not, we can multiply through by something, and every single term in the entire equation, multiples, remember, have the same solutions, that will make opposites. So that's kind of step one. So really, this could be you're multiplying one equation or maybe both equations by whatever appropriate value you need to make opposites. Sometimes, like I said, you don't have to multiply by anything. They're ready to go. But if they're not, you need to make opposites. So say you have a 3 and a 4, you might need to multiply one equation by 4 then, and the other one by -3 or -4 and +3 to make those opposites. So it could be no equations you have to multiply, or it could be one or maybe both to make those opposites. All right, second thing then, we add those two equations together to eliminate the variable. So we're trying to get rid of one of the variables. Why? It's really hard to solve for when you have two letters, right? We need to be able to isolate a variable to get it by itself, to get that value. So we need to only have one variable in our equation. So by eliminating one of the two, we're able to solve for the other one. So by adding those two equations together, that's where we eliminate or get rid of one of those variables. All right, then on to the next part where we can then literally solve for that other equation, or that other variable, pardon me. So when we only have one variable, we can solve for the one that is remaining. So the beauty of this is we have gotten it down to something that we're very familiar with. We can solve the equation for that remaining variable. Awesome. Now remember what these solutions are. If we have two linear equations, the solution is going to be the point that they share, that intersection point potentially. So we're looking for an ordered pair, an x and a y, if we're using x and y. So we need two parts to our equation. Well, we've only just solved for one piece in the ordered pair. So after we have that one part, guess what we do to find the other one? We do what we did in the last section. We, like what our book would call it, back substitute, or we substitute that value back into either of the original equations and solve for that other variable then. So say we've solved for y, we plug that y value back in and solve for x, or vice versa. So we back substitute to solve for the other part of our ordered pair. So once you've back substituted into either original equation to solve for that other variable, then we have our potential ordered pair solution. What we should always do kind of as a last thing just to be sure is we should check that solution. So we should check the solution, that ordered pair, into either of those, or well, actually technically you should do it in both original equations to make sure it is in fact a solution to both. Hopefully that's a quick check and we can just double make sure that we haven't messed up our arithmetic at all. So we check the solution in those equations. So that's sort of the process of elimination. It works really well, especially when we are looking at equations that are in standard, linear equations that are in standard form. All right, so the operations that can be performed. So what's mathematically legal in a system of linear equations to get an equivalent system? So in order to be able to do all those things, we have to realize what's okay to do. So here are some of the operations that are totally fine. One thing that you can always do is you can interchange two equations, like which one's on top, which when you write it, and then the bottom, you can move them around, you can interchange. That's totally fine. That will give you an equivalent system. So that probably makes sense. It's kind of like when you write a solution, you could say x equals 3 or 3 equals x. Those are equivalent answers. It's sort of the same deal. So if there's one that looks easier for you to have written first and then versus below, totally fine. Another thing you can always do is you can multiply an equation by a non-zero constant. So I mean, if you multiply by 0, that doesn't really help you a whole lot. You just get 0 on both sides. But any non-zero constant, as long as you multiply everything in the equation by the same number, you're going to get a multiple of that equation. They are going to have the same solutions, the same ordered pairs as solutions. So it is always going to give you an equivalent equation as well, which is why it's okay to do that when we do elimination. Just be sure when you're multiplying by a non-zero constant that you don't forget to multiply both sides. It's usually pretty obvious to people to multiply the side with the variables, the x and the y, but sometimes we forget. Whoopsie daisy, we got to do the constant on the other side as well. That's a common error that people make. The third thing that we can do that's an equivalent equation is we can always add a multiple of one equation to another equation to replace it, which is what we're doing when we add the two equations together to make that new equation. So when we add those two equations, we get an equivalent equation that comes from that. So when we add them, it is a completely legitimate mathematical operation to do. So all of the things that we do to solve by elimination, we can do with an equivalent equation and will be completely fine. Another way to think about solving, so elimination is great, works awesome. We're going to practice that and do that. It's going to make what we call an equivalent system. So an equivalent system is a system that has the same solution as the original. So that's the key thing when we're thinking about this, is that the solution that we get will always be the same as the original. So I'm going to add right up here, I know I underlined equivalent system, that word, that means that systems that they have the same solution. So the system has the same solution as the original, super important. All right, so we know about elimination. And we also talked in section 1 about using a graph to help you solve. And so we are going to think about graphing as continue to be like a similar way that we could solve. I want you to pause the video, think about or look back at your notes if you need to. How would you, if you had a system of linear equations like this, would you use your graphing calculator? Because you probably wouldn't graph it by hand, right? How would you use your graphing calculator to solve that? Just kind of as a refresher for yourself, and then come back and see if you have the steps that you could potentially use either to solve that way or check if you wanted. All right, so hopefully looking back at your notes, we're going to look for a situation where we have a y equals when we use when we use graphing, because that's how we have to enter it into our calculator. So if they're not solved for y already, you would have to solve them for y. Then you'd have to put both of them into your y equals and then graph it. Make sure you have a window that works. So you have to make sure sometimes you might have to adjust the window. So something to check for if you're not seeing that solution point, especially in real life situations. And then you've got to look for that point of intersection, which is under the second calculate. So looking in your graphing calculator, second calculate menu, and then you look for intersection. So it's an option. It's a way that you can solve. So that's a good way to check as well. So here's what we're going to do to kind of finish off our day 1 for the solving part is we're going to solve some of these by elimination. So we're going to practice that method, and then we're going to take a look at what do we call these different names of solutions? What are some of the words that we use to describe the different kinds of things that can happen when you solve a system of two linear equations? So we'll name them. All right, so first one. So I want you to take a look. They are set up in standard form, so something to watch for. So when I look at equations, this is definitely set up for something I would consider to be an elimination because they're in what we call standard. So ax plus by equals c. So the x and y are on the same side, nice numbers. So I would probably use elimination. So I would look for what would be the easiest to eliminate. Do I want to get rid of the x's or the y's? There's no wrong answer here. Both will work. Some of them might be easier options than others. So I want you to pause the video, think about how could you make opposites with either the x's or the y's. Think about both. What would you have to do? And what do you think might be better? Okay, so hopefully you thought about that. The x's, it's a 3 and a 4. You'd probably want to make one a positive 12, the other a negative 12. So multiplying the first equation by 4, maybe the second one by negative 3, or the first one by negative 4, the second one by positive 3. Great. But if you look at the y's, one of them is already negative. So for me, that's kind of a big indicator that, hey, that one might be easier. And it's negative 2. What if I made the top one a positive 2? Then they would be opposites already. So I look for what's the easiest for me, the least work. So the path of least resistance here. So I would probably multiply the entire first equation by a positive 2. I can replace that equation with that new version, and then I will be able to eliminate the y's. So that's using those equivalent system things. So kind of my step one, just to make sure I'm keeping track of what I'm doing. I'm going to multiply the first equation, so equation 1, by 2. So if it's helpful for you to kind of like write it out, like what am I doing? And notice the way I wrote it, I put parentheses around the whole thing. I'm multiplying 2 by everything. Don't forget the constant. So you have that 18. Now remember, the second equation in this situation anyway, we don't have to do anything with because it's opposite. We've already made opposite. So then I can go ahead in step 2 and I can add those two equations together to eliminate the variables. So I'm going to add the equations. So if I add those two equations together, it looks like I will get 10x. Oh, look, no y's, and then a positive 17. So I would get that that value for that first part of that equation. So I don't usually write the 0y. I'm just writing it so you can see that we have eliminated that variable. Technically, I'd probably just write that. So awesome. So now we're ready to go ahead and solve. So step 3, again, if you're trying to kind of keep track of what you're doing, you're going to solve for x. You're going to solve for that variable. Now, I know it's not a great number. Sorry. They don't have to be nice numbers, but it's okay. So we get a value of 1.7. So that is our value for x. Now, what do we do after we have one part of our ordered pair? So remember, our solution to the system is supposed to be a point. I have an x value. I still need my y. So step 4, I guess, is we need to back substitute, right? So I'm going through our step-by-step that we talked about at the beginning here. I'm going to back substitute. I'm going to put that 1.7 back into either of the original equations. Now, it doesn't matter which one you want to use. Pick the one that looks easier. For me, if I'm looking at equation 1 and 2, I'd probably use equation 1. To me, that looks a little bit more friendly. So 3x plus y equals 9. I'm going to go ahead and substitute in that value of 1.7 in for the x. So I'm going to replace it and solve. So I'll give you a moment to go ahead and do that. So do your calculation and come up with y. And it looks like to me, I got 3.9. So hopefully that checks out for you. So now we have the second component in our ordered pair. We have the 3.9. So we have our solution set, our value. So we could replicate this whole thing on the graphing calculator and we would be able to get that as well. I think this arithmetic is honestly faster than trying to solve both of them for y and do the substitution with fractions and all that kind of yuck that happens when we have to solve. Checking our answers. So kind of remember our steps that we talked about for our solving our system. We did everything through number 4. Now we need to really check that solution. So I would plug in both of those values and see if they work. So in equation 1 and equation 2. Now, if you're pretty confident, I know we don't check all the time, but technically we really should. So step 5 would be the check. Take a moment, just do it on your calculator even, and make sure that that solution works in both. So our check would involve substituting in the 1.7 and the 3.9 in equation 1, which is my work that I have shown on the top here, and then doing the same thing in equation 2, and just verifying that, yep, yes, indeed, that does actually work. So that's the elimination process. That's what we do. It's a great way when we have these two systems of two equations and two unknowns. It's a nice way to do it. All right, so take a look at example 2. We'll try a couple more here and just make sure that we're doing okay. So I want you to take a moment, take a look at the two equations again. Think about which might be easier for you to eliminate, either the x or the y, and then we'll solve. So we really have two options. We can get rid of the x's by making them a 4 and a -4. So that would involve multiplying the equation 2 by a -4. That would work great. The other option would be making the y's opposite, and that would be a +3 and a -3, which would involve multiplying the top equation by +3. Now, you know I'm a positive person. Smile, smile. So I always try to multiply by a positive if I can. So it just makes it a little bit easier to maybe not mess up signs and things like that. So I guess for me, I would probably multiply that first equation by 2, just because I think, or pardon me, by 2, help me, by 3 to make opposites. Woo. So we want to make sure that it's an easy operation, but there's nothing wrong with multiplying the second one by 4. That'll give you the exact same situation. All right, so when we multiply that first equation by +3, we get that replacement equivalent equation, the 12x plus 3y equals -9. Now, I didn't have to do anything with equation 2 again because it was already opposite just by doing that. So I can go right on to my step number 2, and we're going to go ahead and add those two equations together. So we're going to go ahead and add and see what we get. So we'll get our total. And again, what should happen is you should have one of the variables eliminate, which in this case is the y's. And again, I don't normally write that, so I would normally just say our 13x. I wouldn't say anything else. I wouldn't put the +0y. Now, I wanted to do one like this. Look at the other side. It's a 0. Is that okay? Yes. 0 is a number. It's totally fine. So don't be alarmed if you see 0. All that means then is when you solve, so step 3, and again, I know we don't usually kind of write out our steps, but when we solve for that variable, yeah, it's just going to be 0. 0 divided by 13, 0. Cool. That means your solution, your ordered pair, one of the values is 0. That can totally happen. You can be in an axis, so don't be alarmed if you see a 0. All right, what do we do to get the other part of our equation or our solution? We need to back substitute, remember. So step number 4, we are going to substitute back, and we're going to put 0 into either of those original equations to solve, so you can decide which one makes the most sense to you, equation 1 or equation 2. So go ahead and pause the video, back substitute, see what you get for your y value. So I don't know which one you chose. I chose equation 1 just because I thought that might be a little bit less to deal with. There's no negative sign, which again, anytime you can eliminate signs of an issue is great. And when I substituted back in that 0, 4 times 0 is just 0. So you get your y equals -3. So we have our solution point. We think that these two lines are going to cross at the point 0, -3. So again, the last thing we should technically do, step 5 here, sorry, kind of going around in a circle, is we should check our answers. So we should substitute those two back in and see if they work in both of the original equations. So taking a look and substituting in, I put in the 0 for x and the -3 for y, and that definitely checks out for both of those equations. So it is a solution to the system, so it works really well. All right, we're going to do one last solve by elimination before we talk about just the naming part, which is pretty easy, just like actually naming what kind of situation is happening. I want you to take a look at this. So this is in your additionals, and I want you to kind of do a little bit of thinking. What variable do you think would be easier to eliminate? Because again, imagine if you're going to do this graphically or by substitution, solving for y would not be pleasant. You're going to have some yucky numbers to deal with, very mathematical term, and we don't want to have to probably do that. So elimination is going to be easier. So look at the x's and the y's, think about your different options. What could we make opposites? And what do you think might be easier? So go ahead, pause the video and give that a think. All right, I labeled mine equation 1 and equation 2 again, just so we can use that for conversation. What were you thinking? So I'm looking at it at the y's and thinking those are already opposite in sign. So I guess my preference would be to do the y's. Make one +10, make the other -10. Could you do the 3 and the 7 for the x's? 100%. Will you get the same answer? Absolutely, as long as you don't mess up your arithmetic. We want to make sure one would be positive 21, one would be negative 21, multiplying by a 7 and a 3, one's positive, one's negative. Great, absolutely. But if I do this with the y's, then I don't have to worry about the sign. It's already opposite in sign. So just personal preference. So I'm going to go ahead and multiply that first equation by a positive 2, and I'm going to multiply the second equation. I'll just do two different colors here. By a positive 5 to make those y's, one a positive 10 and one a negative 10. So go ahead and do that if that's the way you want to do it. If you want to do 3 and 7, great. It just won't match with the video, but you go ahead and you do you. All right, so once you've multiplied the first equation by 2 and the second equation by 5, what you'll notice is your y's are opposite. So we can go ahead into our step number 2, which is add. So we've made opposites, so now we can add those two equations together to replace that original system. So when I add those two equations together, I'll get an equation that only has the variable x in it. So that's the reason, again, that we're using this solving by elimination. So we can add them very easily together, and then we can go ahead and solve. So solve for x. So we divide by that 41, and we will get our solution for x. Now remember, they're not always going to be nice numbers. In this case, they are, because we're trying to have things that are easy to work with for you. But again, real life situations can be really, really yucky looking. So we want to make sure that we can practice that and do that in an easier way, just to know the process. All right, so after we solve, remember, we only have half. That's only half the solution. So my ordered pair is an x and a y. So I need to find that other one. And you could be solving for an x first or y. It doesn't matter. Just depends on what you eliminate. But step number 4, we need to back substitute, right? We need to plug that number back into either of those originals. So take a moment, make sure you pause the video. Which equation would you substitute that x equals 2 back into, and why? Think about what might be easier for you. So if you look back at them, maybe you netted out the same thing. I think I would use equation 1, just because equation 1 has all positive values. You know me, I like my positives, and then I maybe won't make some of those substitution issues with dealing with negative numbers. So go ahead and solve for y and then see what you come up with. All right, so hopefully we're on the same page there. We get y equals 2, so we have our complete solution. Coincidence, it ended up to be 2, 2. It would not have to be the same number, obviously, for both of those values. So sometimes we have to multiply both equations by a value to make opposites. Sometimes it might just be 1, and sometimes they're opposites already. It just depends. So that's the process of elimination. All right, so the other little piece that we want to chat about today before we wrap up day 1 is to talk about how we interpret graphically what can happen with two linear equations. So I want you to think about, when you graph two lines, what are the possibilities? So we have to think about what could happen when we graph those two linear situations. So we want to make sure that we're thinking about what possibilities there are. So here's what I'd like you to do. In that open space that you have below here, I'd like you to think about what can happen if you graph two lines on the same coordinate system. Most of the situations, if you think about what would happen if you graph two lines, probably a lot of you would come up with right away that they would maybe do something like this. So we have a line here, we have a line there, and where would the solution be? Well, it would be the point that is shared, which would be right there, that ordered pair, that x, y. It would have a solution. So it intersects at a point. In that situation, if it intersects at a point, the key reason that that's happening is because the slopes are different, right? When we look at those two linear equations, the slopes are different. So they are going to end up somewhere crossing. Now, it's not always when you can see it on your graphic calculator screen, but somewhere they are crossing, because if they don't have the same slope, they will eventually intersect somewhere. So we're going to go back and name this type of system, but that's probably the most common thing that happens with two lines. All right, so now I want you to imagine and see if you can draw. There's actually two other scenarios that could happen when you graph two lines. Now, this is where their slopes are different, so that maybe gives you a hint. So pause the video, think about what other two ways could we imagine a system of two lines. Well, hopefully some of you came up with kind of version 2 here. What if your slopes are equal? What does that mean? If your slopes are equal, that means you have parallel lines. So if it is parallel, that means they don't cross anywhere, right? So their slopes are equal. So the slopes are exactly the same. Well, if their slopes are equal and they're parallel, that means they never intersect. And if they never intersect, guess what? They don't have a solution. So there's no solution in that situation. So we can't have any points in common. They aren't sharing anything. So we have looked at kind of two scenarios thus far. The first one is exactly one solution. So we had one solution point, one ordered pair, that point that was in common. The second one, there is no solution. There's no way that we're going to have any points in common. They don't intersect. Is there a third option? And actually there is. Maybe some of you thought of this. What if your slopes are exactly the same and your y-intercepts are exactly the same? In other words, they are exactly the same line. So both equations are identical. They have the same slope and the same y-intercept. So the slopes are equal and the y-intercepts are equal. What if both of those are the same? Well, then they have every point in common, every single thing. And that would be exactly an infinite number of points that they are going to share. So this would have infinite solutions because it would be every point on that line. So we have infinite solutions. So there's sort of three different kind of camps that we can fall into. One solution where it crosses at a point, no solution because they never cross at all, or infinite solutions where it's every single point on that line that's going to have a solution or be working in both. So we have kind of three different options. So I'm going to kind of go up to this original one, statement. It says if a linear equation has two different solutions, then it actually must have, I'm going to go ahead and fill it in, infinite solutions. You can't just have 2 points in common with 2 lines. It's either you have 1 point in common or they have everything in common. Those are your kind of your two scenarios where you talk about that. So I have sort of a kind of a follow-up, just maybe a more clear way to just to be able to say everything, make sure you have all the information that you need. So the number of solutions, if you have exactly one solution, the 2 lines intersect at a point and the slopes of the 2 lines are not equal, they don't cross. If you have infinitely many, in other words, they're the same line, the 2 lines coincide. That's another fancy way for saying they're identical. It's the same line. The slopes of the lines are equal, and their y-intercepts are equal as well. So I'm going to kind of add that to that list. And if there's no solution, doesn't have a solution at all, the 2 lines are parallel, the slopes are equal, but they must have different y-intercepts then, right? So when we think about what those would look like. All right, so we can go back and sort of categorize our situations that we solved earlier today and put names on these. So when we can think about all the ones that we did today have exactly one solution, there are actually names for that. We're going to talk about what that looks like. Right, so there's 2 terms that I want to address here and have you add underneath where you have your conversation about what these graphical interpretations mean. One word is consistent, and then the other word we're going to talk about is inconsistent, just so you know the difference between those 2 words and what they mean in this context. So a consistent system just means it's a system that has a solution. A solution exists, either in this case, a singular point, an ordered pair, or infinitely many, because remember 2 points can only, or 2 lines can only either share 1 point or every point. There's nothing in between. It's one or the other. So a consistent system then would be exactly one solution. That would be consistent. And then the infinitely many solutions, that would be consistent. So I'm going to go back on our pictures that we drew. So that first scenario right there where there's one solution, I would call that a consistent system. So I'm going to go ahead and go back and label these. Infinite solutions then would also be consistent. That just means the word consistent, if you think of something that's consistent, makes sense. This means it has a solution. All right, so what does the prefix in do to a word? It means not. So if you say the word inconsistent, it means it's not consistent. Well, if it's not consistent, guess what that means? Doesn't have a solution. So there's no solution to that system. Well, that would be our third scenario then. That's when our lines are parallel. That would be inconsistent. So I'm going to go back and label that on our pictures that we drew here before. So the parallel lines would be inconsistent. All right, so one of the words that we can use to describe a system is consistent versus inconsistent. Either it has a system or a solution or it doesn't. So most of the time people are okay with that. We can also describe when you do have a solution, how many you have by using a word as well. So we're going to get into those definitions. So this first part, it says a consistent system with exactly one solution is called independent. So we can kind of break down a consistent system into two different categories. So if you're consistent, you can either be independent, that means you have one solution. Well, think about what the word independent means. You stand alone, I'm independent. Or a consistent system that has infinitely many solutions. So think of like the same line scenario. So this one solution would be crosses at a point, so one solution. But what if we have infinitely many? Well, what's the opposite of independent? Dependent. So we have dependent systems. So consistent, you can kind of think of it as there's two different options. You can either be a singular solution, you stand alone, you're independent, or consistent systems can be dependent. So I'm going to go back and we're going to label that as well. So for our consistent ones, we said consistent, one solution for that first picture here. That would be an independent system because it stands alone. There's only one solution. The one that was consistent that had infinite solutions, we would call that dependent. So if you're a consistent system, you're either independent or you're dependent. That's kind of the other part. If you're inconsistent, you're just inconsistent. Like you don't have one. You don't have a solution. All right, so we got to make sure we know what we're looking for. So those are the kinds of systems. So let's take a look at this scenario. Graphically, it's really easy to tell if something is consistent or inconsistent because we're looking at the picture. So we're going to start there and see if we can figure out what that looks like. And then we're going to come back and talk about those two scenarios that I have highlighted on that same page. So I want you to look in your additional notes here. We're going to take a look at this. I have three examples. I wrote the equations as well, just so you can see that these come from equations. They have been graphed. These systems have been graphed for you, which is really nice. I want you to talk or pause the video, and I want you to think through, do these systems have solutions? And if they do, what do you think the solution might be? And how would you classify it? We call that. Would you say it's consistent or inconsistent? Would you say it's, if it is consistent, is it independent or dependent? So go ahead and pause the video. All right, if we can trust the graphs, it certainly looks to me like letter A is, I guess the graphs are I, looks like they're the same line. I guess it's letter A. And if we look at that, if you multiply this first equation by -2, will you get the exact same equation? So we have to do a little bit of matching here first to see which equations match which pictures, and then we'll be able to tell. So let's see what happens if I multiply this first one by -2. So that would give me a -4x and then plus 6y and equals -6. So not exactly the same equation. So that doesn't match with letter I because that needs to be the same line. Both, everything would have to be the same about it. So let's keep going and see if we can find the one that is the same line that would match with letter I here. Let's try this last one. What if I multiply this by -2? I'd get our -4x plus 6y equals -6. Ooh, there we go, identical. So it looks like letter C matches with I. Those are the same lines. So we're matching like the solution with the graph. Now, how would we label that graph? So C goes with I. So C goes with I. What are we going to call that? Well, if they're the same line, that means they have infinite solutions. So we have an infinite number of solutions. And what would you classify that as then if they're infinite solutions? If it's infinite, that means it is consistent. They actually have solutions. And because there's a whole bunch of them, that would be dependent. So that system would be consistent and dependent when we look at that value. All right, so now we need to find another match here. So let's see if we can do that. This first equation, we ended up, let's see what would happen. It looks like the x's are the same and the y's are the same, but what was different was the number on the other side. In other words, if I add these together, I would get two equations. Like if I add these together, I get 0 equals 0, right? So when I had the ones that were exactly the same equation, if I add the two together, I would get 0 equals 0. If I do this first one and I add them together, I would get 0 equals 12. Well, that doesn't make a lot of sense, right? So the one that worked, the one that gave me the exact same equation, which would graph as the same line, I got a statement that was always true. Like that would always make sense. This one, when I had the two together, I got a statement that was absolutely false. It would never make sense. So think about this for a second. If you solve it algebraically and you get a statement that doesn't make sense, what do you suppose that means for your graph? Well, there's probably not going to be a solution, right? So let's see which graph looks like that. Which graph shows us no solution? So it looks like, I'm going to use different color here. Looks like this one looks like it's the parallel situation, right? This number like 2, I guess. Parallel, that would be no solution. Well, that would make a whole lot of sense then looking at this letter A, because that one doesn't make sense. You get 0 equals 12. That is no solution. So if we graphically don't have points in common, that means the algebra has to show no points in common as well, a statement that is false. So that means letter A is going to match with number 2 here. That is no solution at all because it was a parallel line. We would call that system inconsistent. So what we see algebraically should always match with what we see graphically. So if you have no points in common, that has to be something that didn't make sense algebraically. Okay, so I'm just going to kind of erase that so we don't have our color coding. Let's see, that should be, I guess I wanted that to be red still. There we go. So the reds match up and the blues match up. All right, now what does that leave us with? Let's take a look at the last equation. So if I multiply this bottom one, I'm just trying to get the equation, see what's happening. I'm going to multiply the bottom one by 2. That would give me 2x plus 4y equals 10. If I'm going to try to solve by elimination or whatever, or maybe I'd multiply by -2 to see if I can eliminate. That would be -2x minus 4y equals -10. Probably should have done that right away. When I add those two equations together, you would get, looks like a -7y equals 7. And then we would get, or -7, pardon me, we get y equals, divide by -7, 1. We get a solution. We get a point. Now, we could keep going and we could solve the rest of that system algebraically. We could do it with elimination. But what I want you to be able to see is you actually get a single solution there. These are not the same equations. They do not have the same slope. So another kind of way to solve these is you could solve every equation for y and see the slope. But I was just trying to do it by elimination. It looks like I got a y value of 1, which sure looks like this last graph right here. So I think this letter B has to, of course, because there's only one left, match with number 3 here. So letter B is going to match with 3. And what do we see in this graph? We see one solution. So we have a singular solution, which means the solution exists. So it is consistent. And what do we call it when it has a singular solution? We call it independent because there's just one. So it's consistent and it is independent. So when we're looking at these values, we're trying to decide what to call that system. I would say consistent and independent. And I guess I would say that's 3-1. And if you substitute back in, you can solve that. So being able to recognize what kind of solution you have is really important. We need to be able to recognize it graphically, which I think is pretty easy. I can tell right away that the letter number 1, that was the same line. Like, yep, that's what that looks like. That means there's infinite solutions. That's pretty easy graphically. No solution is pretty easy too because they're parallel. We can see that right away. We have nothing in common. And I think it's pretty easy to tell consistent, independent, one solution graphically. But how do we tell from the equations themselves? We have to look at what happens when we solve them. So that 0 equals 12, the getting an actual value versus getting a statement of truth, 0 equals 0, something that's always true. Algebraically, that's how we know what system we have. So let's go back and see if we can nail this down algebraically. So what if you get a false statement? What if you're solving by elimination and you get something like 0 equals 9, something that is false? What does that mean for you when you're solving a system then? Well, that means that there would be no solution to that system. It does not have one. So that means your lines are parallel. So it's important to recognize it algebraically too. So you would have no solution. That is an inconsistent system. That must mean your two lines are parallel in this situation. Now, we can have inconsistent systems and nonlinear systems as well, things that don't have solutions. So we want to make sure we realize that this is a bigger issue than just lines. What if you get a sentence that is always true? It's true for all values, like 0 equals 0 when you're solving, when you're doing elimination. What does that mean? It means you have the same line. You have infinite solutions. So when you're doing your solving, you have infinite solutions. That means we would call that consistent and dependent then, right? Because remember, there's infinite, we depend on each other. Think of what dependent means. There's a whole bunch of them. So that means, in other words, you have the same line. Now, in nonlinear systems, that could mean a whole bunch of different things too. But if we have statement of equality, it means it's always true. So those are kind of your two sort of extremes. Otherwise, you'll just get your singular solution that we always have. So I want to finish up practicing that, looking at a system, being able to figure out, hey, how many solutions does this have? I don't want you to have to graph it to be able to tell. I don't want you to have to look at the slopes and the y-intercepts. We should be able to tell from elimination as well. Although you could definitely, again, solve for y and look at the slopes and y-intercepts. If the slopes are the same and they have the same y-intercept, same line. If the slopes are the same and they have a different y-intercept, they're parallel. If they have different slopes, then their different lines are going to cross at a point. Yes, that works, but we should be able to do it this way too. All right, so here's what I'd like you to do. I want you to try to solve this system and then classify it by what you see when you do that first step. So again, I'm going to say my 1 and 2 here. If you were going to eliminate a variable, what would you do? So pause the video, do your elimination, see what happens. Probably either way you slice it, whether you're trying to get rid of x or y, you'd multiply that first equation by 4. So we'd have 4x minus 12y equals 8. My second equation stays exactly the same. Now what I want you to see is what happens when you do step number 2 now. Step number 2, remember, is we add those two together to see what we get. So we're going to do an addition here. We get rid of the x's and the y's, and what's left on the other side would be 16. So you get the equation 0 equals 16. Now I want you to think about what that means. 0 equals 16. That is false. That is not true. So what does that mean for our system? That must mean that this is an inconsistent system. False sentences mean we do not have solutions. So inconsistent, there is no solution here. So what do we know about the lines? They must be parallel. These must be parallel lines. And if you look at their slopes, they are exactly the same. So if you solve each of these for y, you get the same slope. So be sure that you're always looking at algebraically and graphically what these things would mean. So those consistent and independent, consistent dependent versus inconsistent. But elimination, a great way to solve those equations where we had 2 equations, 2 unknowns, linear. So tomorrow in day 2, we'll take a look at another warm up of this and then some applications.